Okay, so the first issue that I found on here, guys, was that a few people, and this is kind of my fault because I didn't tell you this, went and got their data, or went and got data off my website to compare to theirs and found that theirs looked completely wrong. Okay, as a result of looking at the data, because they went into AP Science 10 Notes and Assignments, and I have not uploaded anything new to that folder in a long time. I uploaded it only to the regular Science 10 one, so that was my fault. But what I did is, if you had the that observations chart, I just looked at those observations and then checked your pairs and saw if they matched up with the observation chart that you had. Okay, so you didn't lose any marks if that happened. Okay, I just had to kind of go through your observations and double check rather than just go, I know that they're supposed to go in this order. Okay, so it still worked out, but that was one place where I think people got confused because I got a bunch of emails the night before. They're like, oh, Mr. Codere, my results look all wrong. I'm like, I don't know how that can be, but anyway, that's how it could be. Okay. In the future, guys, I'll try and remember to upload also to there. Okay, so that the most current results are up there as well. So that one was my fault. Okay. Science 10. Okay, so we got the properties of compounds here. The problem obviously has to be restated in your own words in the form of a question. Okay. And the manipulated variable. Okay. These were given out, guys, and so I'm sticky when I mark these kind of things. If I know that I've essentially given that away in class, I'm harsh when I mark. Okay, and the variables were one of the things that I gave out in class. So if your variables weren't right, you probably got a comment that said your variables aren't right, and I gave them out in class, and they're recorded in the podcast. You need to make sure that you take better notes on the day of the lab, or watch the podcast while you're putting the lab report together. You should do number 2 anyway. Okay? Really. How many people watch the podcast while they're putting their lab report together? Okay? I should see everybody's hand up next time. It's not cheating. It's smart. Okay? Because did I give lots of stuff away in class? Okay? If you doubt me, go over your lab tonight and watch the podcast that we made. Actually, we made 3 of them. Okay? In preparation for that lab. If you watch them, you'll find that I practically gave the whole thing away. All right, so you definitely want to watch those while you're putting your lab report together, because they'll remind you of little things, all those little hints that I give out in class that maybe you missed or didn't copy down, you get again. All right, so you definitely want to do that for future labs. All right, so the manipulated variable was the unknown substances, okay? And they are the manipulated variable because the experimenter will be running the same series of tests several times, each time on an unknown substance with unique properties, okay? I said what it was, and I explained why, right? And that's what you have to do for each one, all right? The responding variable was the results of each series of tests. In other words, the physical properties, okay? They will be unique to each substance, and so will respond to whatever unknown material is being tested, all right? A lot of people used the word reactions in this variable, okay? There were no chemical reactions going on in this lab. Okay? All we were doing was finding the physical properties. Right? Had there been chemical reactions going on, there would have been, like, radical color changes and precipitates and all those things we talked about the other day that are the signs of a chemical reaction. We didn't have any of those. All right? If we'd have had those, we would no longer have been testing the physical properties of the substance we thought we had, because in a chemical reaction, you change the substances. Agreed? Right? So I know that seems kind of nitpicky, but it's kind of an important detail. All right, and then the controlled variables, how many of these are you supposed to have? 3. Okay, got to have 3 of these. All right, so the test being performed, those have to be controlled because in order to compare results, each material has to be tested in the same way. All right, I wouldn't run, just a solubility test and a pH test on one thing and then just a conductivity test on another. Right? That wouldn't be a fair way or a controlled way to run the experiment. All right, temperature, because it can affect the results of the tests and many physical properties like solubility. All right, now, we didn't actively control the temperature, but I mean, climate is controlled within the school to within a few degrees, and so that's good enough. All right, and the amount of each substance, as this could affect the interpretation of the results of many tests. Okay, distilled water was being used for solubility tests to eliminate the effect of minerals on the physical properties. So I actually listed 4. Okay. Questions on the variables? All right, so you can see here, about how long each one of those should be. Okay. All right, for our hypothesis, this people really had struggled with. Okay, what's the if part supposed to talk about? Yeah, sort of what you're testing, but more, it's talking about this. It's talking about the problem. Can unknown samples be identified by only their physical properties? Well, if I want to say that that's true, I'd better say that if all compounds have unique combinations of particles influencing their physical properties, or you could have just said if all compounds have unique physical properties. Okay? If that's true, and we do what we did in this lab, we should be able to identify them all because they'll all have their own unique set of data. Agreed? Okay? The premise of this lab was that all compounds have unique physical properties. If that premise is wrong, everything we tested would have exactly the same data. All right? And that's not what happened, is it? All right? So the if part of your hypothesis needs to deal with the premise you are working on, what you think is true. All right? That's what goes in the if part. All right? I had a lot of, if we test a bunch of unknown substances, I had a lot of hypotheses that started that way. Okay? That's the experiment. You're talking about the experiment. That goes in the and part of the hypothesis. Okay? The and part talks about the experiment. The if part talks about what you think is the answer to the problem, or is the premise that you're working on, or is the cause of whatever phenomenon you're studying. Okay? Does that make sense to everybody? It takes a while for people to get how to do hypotheses. Okay? So don't get too down on yourself if you didn't do well in the hypothesis the first time. Okay? On the plus side, there were a lot of ifs, ands, and thens. They just weren't always in the right kind of order, okay? But at least everyone kind of had it there. All right, then materials and procedure were already on there for you. Well, sorry, materials were. You had to come up with the procedure. Now, we needed a numbered list, okay? A procedure needs to be a numbered list, and it needs to have breaks between the steps. Because if you're running these steps, you're going to do one step, and you're going to look away from your sheet. Okay? You want to be able to quickly come back and find where you were and move on to the next step. That's easy when the steps are organized like these are. It's difficult if it's a paragraph, because then you essentially have to start at the beginning of the paragraph and read all the way through until you get to where you were before. Right? And it takes longer that way. Right? So a procedure is always written up as a numbered set of steps with breaks between each step. All right? There needed to be detail there. Okay, we need to have a lot of detail on how do we do this stuff. Well, the first step, collect the depression plate, thermometer, stirring rod, conductivity apparatus from the front table. I even told them where to get it from. Okay, take equal amounts, approximately 1 gram. We said fill it 1/3 full. That would be fine too. Okay, of each unknown and place them in separate depressions on the plate. Okay, I mean, you can't take for granted that people are smart. I actually told them don't put them all in the same depression. Okay. You just can't assume anything. All right, record the following observable properties in a chart. Color, texture, okay, and by texture I mean crystalline, waxy, or molten. Okay, state of matter, solid, liquid, or gas. Waft the samples and record any odors or any other characteristics you feel are important. Okay, so that even gives the experimenter a little bit of personal leeway. All right. Fourth step, using an eyedropper containing distilled water. We use the wash bottles. Okay, fill each depression to within 3/4 of full and stir briefly while taking the temperature of the mixture. Record whether the material is soluble based on color changes, changes in the crystal's shape, or any separation of the materials. Okay, I had a lot of people on the solubility test who just said, add water and record your observations. What if the person doesn't know what solubility is? Okay, we have to explain. Here's what to look for. Here's how you'll know if it's soluble. If the crystals shrink, change shape, if the color of the water changes, okay, or if there's any separation, if one thing floats on top of the other. All right, those are all signs, okay, to look for. Okay, then take the conductivity apparatus, okay, and place it in the solutions created in step 4. Press the button and record the reading shown on the face in your chart. Now, I should have said in there, and I didn't, that you should rinse it between samples, and I did not say that in mine here. Okay, using either pH paper or an electronic meter, record the pH of each of the solutions. From step 4, by placing either the strip or the meter in the solutions, compare the color of the strips to the color code on the pH paper container, or record the number shown on the electronic meter. We tried electronic meters last year and just didn't work very well because we didn't have enough sample and it fit in very well. Okay. All right, and then number 7, repeat these steps for all the unknown compounds. Okay, so detailed numerical order steps. Okay. All right, questions on the procedure? Okay. Then you had your observations chart, which basically you just had to fill in your data from the lab. Okay. A was a green crystalline solid that was high solubility, 9 conductivity, pH of 6. B was fine white crystalline solid with no odor, high solubility, 10 conductivity, pH of 1. All right, that was the one I told you. Remember, it was already dissolved in water for you. Okay, was sample B. All right. Clear odorless liquid was C. It was soluble, had no conductivity, and a pH of 7. Pretty easy to figure out what that one was. Okay. D was also a clear liquid, strong antiseptic odor. Okay. Was soluble in water, had a conductivity of 1 and a pH of 8. Okay. E was a red crystalline solid, irregular crystals. Okay. High solubility, conductivity 9. Okay, et cetera, et cetera. So let's figure out what these are. A, green crystalline solid. I don't think I have to go any further than that. What was the only substance on our materials list that would have been a green crystalline solid? Nickel chloride. Okay, that's what it was. All right, for B, fine white crystalline solid, no odor, high solubility, 10 conductivity, pH of 1. All right, if something has a pH of 1, it is a what? It is an acid. The only thing on that list that could be an acid is what? Peter? Hydrogen chloride. Okay, here's why. Acids have to donate hydrogen ions. Okay, and this is the only compound on our list that has a hydrogen that will come off when put in solution. But a lot of people said it was this. Said it was ammonium chloride. When this hits water, what does it separate into? Ammonium, NH4, and chloride. It doesn't separate into hydrogen. Okay, ammonium stays together. All right, so it's not acidic. All right. Okay. C we said was easy. C was water. Okay, what was D? It was ethanol. Okay, the only difference between D and C was the smell. Okay, they were both molecular compounds because they were liquids at room temperature. Okay, so those ones were pretty straightforward. For E, what's the only red crystalline solid on our list? Cobalt 2 chloride. Okay, cobalt's always got red crystals and red solutions. Solid, waxy, non-crystalline, translucent, no odor, not soluble, conductivity of 0, and a pH of 7. Philip? Paraffin. Yeah, that was candle wax. Okay, all I did was take a candle and just shave it into little shreds. Okay, that's all that stuff was. All right. For G, small, off-white, spherical, crystalline solid, no odor. Okay, solubility was good with a temperature decrease, slight. Okay, conductivity of 8, pH of 8. Okay, that is ammonium chloride, or sorry, ammonium nitrate. That's the stuff that's in those little cold packs. Okay, have you ever used one of those where you pop the little bladder full of water, shake it up, and it gets cold? Okay, the powdery stuff inside is ammonium nitrate. Okay, and it gets colder when it touches water. Okay, H, large, greasy, saucer-shaped crystalline solid. Okay, high solubility, conductivity of 10, pH of 14. Okay, all bases contain what? Hydroxide. Now, a lot of people look at ethanol and go, it's got an OH on the end. And it does. I won't argue that. Okay, it only looks that way though, just the way it's written. The O and the H actually aren't connected. Okay, and this is a molecular compound, is it not? All right. So does it split when it gets into water anyway? It doesn't. Okay. So this is not basic. Okay. This, however, is. Sodium hydroxide was our very strong base. All right. Medium-sized, clear / white crystalline solid. Okay, solid, no odor. Was highly soluble. Okay, had a conductivity of 2 and a pH of 8. If it had a conductivity of 2, was it ionic or molecular? It was molecular. All right? The only crystalline solid on our list that would have been molecular was, Peter? Sucrose, sugar. Okay, that was the only one. And that was, of course, the thing that separated sodium chloride from sucrose, was the conductivity. Okay, J, small white square crystals, solid, no odor. Okay, high solubility, conductivity of 8. Okay, pH of 6, that was sodium chloride. And the blue crystalline solid was? Ellie? Copper 2 sulfate. Okay, again, the blue crystalline solid gave it away. All right, so that kind of fills in the chart down there. Okay, and that was all you had to do for analysis. For your conclusion, okay, we first off restate our hypothesis. There was a few people who forgot to do that, and it's as simple as copying and pasting it. That's all I did. Okay, I just copied and pasted it down to here. All right, then I have to talk about why I can accept it or reject it. Now, here's what I have to think about. All of my data first. All of my data for every substance was different. Okay, every substance had a different set of results. That's one of the things I predicted, so that's good. Okay, what that tells me is that all things do have unique physical properties, and that was the premise I was working on. So if that's the case, and I was able to identify all the materials, I think I met all 3 parts of my hypothesis. All right, so this hypothesis is acceptable because each of the samples did indeed have a unique combination of physical properties that allowed them to be identified as ionic, molecular, acidic, or basic, and then identified. Okay, so I said, here's my results. They are what I predicted, therefore I can accept the hypothesis. Okay, sources of error. Biggest source of error, and I build this right in. I never change this lab. I do it exactly the same way. I, on purpose, make sure you get small amounts of everything so that you will come up with this source of error. It is highly inconvenient to deal with such small samples. Okay, makes it difficult to do an effective solubility test because you can barely add enough water for even really soluble stuff to dissolve in that tiny little depression. Okay, makes it hard to observe things. It makes it hard to measure conductivity. All of that. To improve this, larger amounts of each sample could be given to each group. Yep, that would be the easiest way to improve the lab. All right, second thing, I always find that common sources of samples for all groups could have led to accidental contamination of the samples. Okay, even though I tell you don't take the scupula from this one and use it in that one, and don't take the eyedropper from this one and use it in that one, I can't guarantee that that never happens. Okay, so it's possible, okay, that the samples could get contaminated. All right, and that could lead to, you know, possibly having poor data, but it's pretty rare. All right, other things, using the depression plate and having the samples so close together could have also led to a contamination problem. Okay, it's possible, and that would have been beyond your control. Okay, things like that. It's got to be stuff that you had no choice but to do the way it was you were told to. Okay, it can't be stuff like, well, we might have done this, and yeah, that could have been a source of error. If you say you might have done that, then you should have double checked and done it again. Okay, that's a source. That's human error. Okay, we don't want to have human error in there. All right, the class discussion questions. It's always a good idea to make note of a couple of these things here. Okay, what was the purpose of testing distilled water? Distilled water was used in the solubility test because it contains no minerals and thus would not affect the other tests being carried out. Okay, obviously we can't test with tap water or we'll get a conductivity for everything. Okay, and that would make it very difficult to identify everything. What were some notable differences between the behavior of molecular and ionic compounds? Well, first off, all the ionic compounds did what? Conducted electricity. Okay? The other thing, your really strong acid and really strong base were both ionic or molecular? NaOH, ionic or molecular? It's got a metal in it. What is it? It's ionic. Okay? Hydrogen chloride, ionic or molecular? Ionic. They were both ionic, right? Things that have generally a really strong pH in either direction, okay, are going to be ionic compounds. Okay, in terms of pH, okay, we just talked about that. Those are the big ones there. Okay, and number 4, what temperature changes did you note in any of your tests? Well, hydrogen chloride and sodium hydroxide both got warmer when you added water to them. They do that. Strong acids and strong bases tend to be exothermic when placed in water. Okay, and then of course you had the ammonium nitrate that got cooler. Okay, questions on any of that? All right, now you're gonna have another lab probably next week. Okay, make sure you have a look at this one and look at the comments. Okay, if I gave any comments to yours, and just remember those when you're going through and doing your next one. Okay. All right.